Okay. So we were talking about the prediction intervals, and we just talked about this probability. Okay. So we just say that, well, the probability that x is between these two values, mu minus z alpha over 2 times sigma and mu plus z alpha over 2 times sigma, that's equal to 1 minus alpha. And for example, we just plug in these values and found that, well, you have this probability. And we said that this probability has two meanings. One, in terms of an individual, which says that the probability of an individual's height is between this value and this value is 0.90. Okay. So first in the individual, and by the second one, we say that, well, this probability is in terms of population, it says that 90% of people are between these two values. Okay. So, um, well, if you don't know sigma, so, okay, we just said that mu minus z alpha over 2 times sigma and mu plus z alpha over 2 times sigma, that's equal to 1 minus alpha, right? So if you don't know sigma, can you write this? Can you write this? So instead of mu, just plug in x bar. If you don't know mu, just plug in x bar. And is this still true? Is this still true that x is between x bar instead of mu minus z alpha over 2 and sigma, x bar plus z alpha over 2 sigma, and that's probably is 1 minus alpha? Well, we have x bar, okay, now in this equation, we have x bar instead of mu, which is a random variable, right? So x bar is a random variable, and it has its own what standard deviation, right? So well, we cannot write this, but we can just adjust it. We can just adjust it as follows. So the probability that x bar minus z alpha over 2 times, so as you can see, we just add this 1 over n, okay? So previously it was sigma times root 1. Now we just convert this to sigma times root 1 plus 1 over n. What is this 1 over n? You can think of this as, remember, sigma of x bar was sigma divided by root n, okay? So what you do is you just add sigma, so this is what? This is sigma times 1 over root n, or in root 1 over n. So what you do is you just add this portion of the standard deviation to here, okay? So this is a 1 minus alpha 100 uh, percent prediction interval of a future observation x. So for example, if alpha is equal to 0.05, then this is the 95% prediction interval for a future observation of an x. Okay. Well, if the random sample comes from a normal distribution, okay, but you don't know the variance, okay? So in the previous one, just like the confidence interval where you know sigma, so we just write the prediction interval where you know sigma. So here in this case, you know sigma, right? You know sigma. But in this case, now assume the case where sigma is not known, okay? Where sigma is not known. So if sigma is not known, what happens to the prediction interval? Just pause the video and think of this for 30 seconds. What happens to this formula? What happens to this formula? So as you might guess, sigma, okay, and z, okay. So what will happen is that the z will return to t and sigma will return to s. You see this? So the formula just remains very same. So instead of t z I have t, and instead of sigma I have s now. So this is the, again, 1 minus alpha times 100% prediction interval when sigma is not known. Okay. Okay, so the third type of interval is called the tolerance limits. So what are the tolerance limits? Just recall our previous probability expression, where mu is equal to 170, sigma is equal to 10, and z sub 0.005 is equal to 100. So this is not 0.005, but probably this is 0.025, right? Sorry for this. This is 0.025. So we say that, well, this probability has two meanings. First one in terms of an individual, and the second one is in terms of the population. okay? And for the individual, we talk about the prediction interval. Now we will talk about the population, okay? So what does this mean in terms of the population? It says that, well, 90% of the population is in this interval, okay? So I'm just extending this expression to make the definition of tolerance limits in a more clear way. I am 100% sure that, right? I'm 100% sure that 90% of the population is in this interval. Okay. I am 100% sure. Why? Because I know the parameters. Okay, I know mu and I know sigma. Well, this probability is just for sure. 90% of the population is in this interval. So in tolerance limits, what I will do is that, so I don't know mu and sigma, hence I will estimate them, which means now I will not be 100% sure, but I will be somehow less than 100% sure. So I will construct an interval so that I am 90% sure that 90% of the population is inside this interval, okay? Now I'm not 100% sure since I don't know the parameters, but I am 95% sure. It can be, of course, 90%, 80%, but the point is that you are not 100% sure, but you are less than 100% sure that some percent of the population is in that interval, okay? So, well, why do we need the tolerance limits? So when the engineering specifications for the output of a process is tight, okay, so the manager will be concerned about the long range performance rather than just next observation. So for example, in our previous examples, we talk about the ball bearings, I Ruhlmann. We were talking about the ball bearings, and well, their specification, their diameter was very important. So you are just interested in so they are interested in the long range performance, which means you are interested in the measure of the population, in the forthcoming population, so that you are interested in the tolerance limits. Okay, so using tolerance limits, in fact, we can. So if we can determine the bounds that cover a large proportion of the population values with a high probability, then that will be very useful to the manager. Okay, so what I need is cover a large proportion of the population, okay, with high probability. That's exactly what this tolerance limit what this tolerance limits just achieve. So the tolerance limits with unknown mean mu and unknown variance sigma, the tolerance limits are given by x bar plus minus k times s. So what is k? K is a parameter, okay? So where you can just claim with 1 minus gamma, okay? So what is gamma? Well, we are just using alpha for one part of confidence, okay? So we need another parameter, which is gamma. So you can claim with 1 minus gamma 100% confidence that the given limit contains at least 1 minus alpha percent of the measurements. So you have a table in your book which gives the values of k, okay, for 1 minus alpha equal to these three values and 1 minus gamma equal to these two values. And for different values of n. Okay, so see, this is table A7. So if you want to be, for example, what is this gamma of 0.05? If you want to be 95% sure, so that your interval covers 90% of the population, okay, and you just take a sample with n equal to 10 items, then this is the k that you should just use for. Okay. So let's finish this argument with an example so that it is crystal clear in your head. Well, a machine produces metal pieces that are cylindrical in shape. Right? So you just take a sample, right? You just take a sample, and it turns out that, so there's a sample. Well, it turns out that the diameters are 1.01, 0.97, up to 1.03. Okay, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9 many samples. Okay, so you will use the data to calculate three interval types and draw interpretations that illustrate the distinction between them. So for all computations, we will assume we will assume that the diameters of the cylindricals are normally distributed. So it turns out that if you just take the average of these samples, the X bar observed turns out to be 1.0056, and the sample standard deviation is 0.0246. Okay, so this is the sample standard deviation of these 9 data, and similarly, this is the sample mean of these 9 data. Now, first find the 99 confidence interval on the mean diameter, then find the 99 prediction interval on the measured diameter of a single metal piece, and then find the tolerance limit. And 99% tolerance limits, remember, so this 99 means that gamma is equal to 0.01, that will contain 95% of metal pieces where it says 0.05, the alpha. So the 99% confidence interval is its X bar plus minus T sub 0.005 times S divided by root n. Okay, X bar is this. Okay, so I just plug in the values. Well, this is S, and this is square root of n, which is 3, and this is T sub 0.005, okay, from the table. So let's see T 0.005. Just look at it from the table. Let me just open it. Okay, so I have the statistics, the book, and the Walpole-Myers here. Okay, so this is the T distribution. So I need alpha 0.005 here, right? 0.005 just here. With 9 degrees of freedom, it's what? It's where? It's 3.2 3.250. Okay, so just go back. 0005. Okay, so am I wrong? It was 005 with 9. No, with okay, with so this is there were 9 samples, so we have 8 degrees of freedom. So this is the answer, right? This is the t value, 3.355. So this is the value that we have. Okay, so this is 3.355. This is the t value. Okay, this one, great. So this is my confidence interval. Well, the next thing is the prediction interval. It's almost the same formula, except what you do is in the square root, you just write 1 plus 1 over n. Okay, so this is in the square root, you have n. So this is just like s times 1 over n. But here you have s times 1 plus 1 over n. Okay. That's great. So, well, so it turns out that the prediction interval for a single observation is this part, okay? That's great. So again, this is for mu, okay? This is for mu. The unknown parameter mu, which is the average diameter, it's between 1.0056 and plus minus 0.0275, and this is the prediction interval. So the prediction interval just says, it says that, well, a single observation, just a single item, the probability that a single item's diameter is between this value and this value is equal to what? Is equal to 0.99, okay? So this is prediction interval, which says the interval is for a single observation, okay? This is for single observation, but this is for mu, okay? For the parameter. And for the last one, we have the tolerance limits. So gamma is equal to 0.01, or 1 minus gamma is 0.99. So alpha is equal to 0.05, and I have n is equal to 9. Okay, so let's go to again, go to the table A7 and try to see what we have there. A6, and this is A7. So I have n is equal to 9. Gamma was, what was gamma? 0.01, right? 0.01, and alpha is this value. So I think this is the thing that we have, 4.550, right? Exactly. This is what we have, 4.550. So this is the tolerance limits. What does this mean? I am 99% confident that, well, this interval will contain 95% of the 95% of the products. Okay, 95% of the diameters of the products are in this interval. Okay? So this is the tolerance limits. Well, so where to use them? Let's make a recap. So for a population parameter like mu, we just use the confidence interval. Okay. So the confidence interval is to estimate the value of mu. So in our case, uh, in the mu case, that's the average of the population. That's the average of the population. That's the parameter of a population. So it's just given by the confidence interval. So a tolerance interval or the tolerance limit is needed if you want to find where a large proportion of a population values will just fall. Okay, so you're just producing some items and assume that if you are producing some items for another factory, for another, let's say another firm, and if they have some tolerance limits and say that, well, if you are above or below this tolerance limits, I won't buy your items. So you are just very curious about your production. So where will our large portion of the population will lie in between? Okay, so the large population, the large proportion of population is very important for you to see how much of your production will be scrapped or not. So to predict the value of a single population member, okay, just one, for example, just one ball bearing, just one student, or just one diameter, then we just calculate the prediction. So, okay, so that's all for the intervals. Let's meet in the next video.